Good afternoon, students. Today we are going to learn very important concept from tree data structure. So first of all, we'll try to know what is data structure. Data structure is a way how we organize the data, store the data in memory so that we can access the data easily whenever it is required. So basically, there are two types of data structures. One is called as a linear data structure and second one is called as a non-linear data structure. So linear data structure means what? Here we are storing the data in some order or we are going to store the data linearly. The examples of linear data structure are array, stack, queue and linked list. We know that array is a linear set of memory storage which is available to us. Stack is a LIFO type of data structure which uses last in first out strategy. Exactly opposite to this queue data structure where we have first in first out strategy. Then we do have the linked list with us. Linked list can be implemented with the help of dynamic memory management. In non-linear data structure we have tree and graph. So out of this particular types, today we are going to discuss about the tree data structure. So first of all, we'll try to know what is tree. So tree is nothing but the set of nodes and the edges. So here you can see this is a particular node, right? So just like a real-time tree, what we have, tree is rooted in the ground and it flourish in the air. Exactly upside down what we are doing here. So node, particularly a node, holds the data and we can traverse from one node to second node in a downside manner. Okay, so this particular thing is called as a edge. If we follow the consecutive edge to move up to the leaf node, then it is called as a path. So here we know that A to B, then to D, then to G and then to J. So this is one of the path. If we consider any edge which is connecting to any two nodes is nothing but the edge. So here is the example, DG is one of the edge, AB is the another edge. Fine. So we'll try to understand this concept using one real-time scenario. What if a student from one class has to tell something to the principal of that particular institute? Then what will be the flow? How that particular person, that particular student will reach to the principal? So first of all, student needs to report his query or his particular thing to the guardian teacher. So guardian teacher will report the things to the class teacher. Then class teacher will report to the head of the department. And through this head of the department, the particular thing can be conveyed to the principal. So here we can understand. So that particular system is flowing from top to bottom hierarchically. So basically tree is a data structure where we use to store the hierarchical data. So here we can easily understand first node is called as a root node. So just like a real tree, there is only one root to each and every tree. So this will behave as a root node and after that this particular B is called as a left child of root and this is called the right child of the root. Similarly, this particular entire tree which is at the left side is called as a left subtree of node A. Similarly, this particular subtree is called as a right subtree of particularly root A. So we know that there are various type of trees. In particularly tree, we have binary tree, AVL tree, red-black tree, binary search tree. So out of that, we will go through the binary tree. So we know that the word binary means what? 1 or 2, right? So any tree, capital T, is called as a binary tree if it have almost 2 children, right? So any node will have either 0, 1 or 2 children. So this particular tree is called as a binary tree. So we can take the examples. So this particular figure A, you can see here in figure A, the root node is A and this particular node A is having 2 children. B is a left child and C is a right child. So total 2 children. So that condition is satisfied. So that's why figure A is binary tree. Similarly, figure B, root node A is having 1 children. Similarly, this is having 1 children and this is having a 0 children. So all the figures A, B, C, D, all the figure follows the property of binary tree. That's why these are the binary trees. So now we'll take one example. What if this is the tree? Whether this is binary tree? So of course not, because this particular node A is having a 3 children, but we can have at most only 2 children, right? So this is the first property. Then what is the second property? That number of nodes, the maximum node that can be possible at each level. So we know that what is level? The root node is always present at level 0. Similarly, the next level is called level 1, level 2 and level 3. So we can here find out the number of maximum elements or maximum nodes allowed here. So it is nothing but the 2 raised to 0. So it is 1. So at level 0, the total number of maximum nodes are 1. Then 2 raised to 1, the value is 2. So at level 1, so this particularly exponential is the 1. So at this level, maximum 2 nodes are allowed. Similarly, 2 raised to 2 at level 2, so 4. Similarly, 2 raised to 3, so 8. This way we can say that in each level k, we can have at most 2 raised to k nodes. So here we'll see the logical representation of the binary tree. So we use the link structure to represent any given binary tree. So particular node of binary tree is having 2 children. One is the left child and second one is the right child. So to represent this particular node, we use the node structure from doubly linked list. So A is the information part. This particularly is pointer to a left child and this is particularly pointer to a right child. So B is the left child of node A, so it is situated here and the left pointer of node A is pointing to node B. Then similarly, C is the right child, so the right child part of node A is pointing to a C. So here similarly, the left child of B is D and the right child of node B is E. Fine. So now here we can consider C is not having any left child. So this child is absent here. So how we can represent the left child field of node C? We have entered null there. So it represents or it indicates that particular node C don't have any left child. Similarly, the F is the right child of node C. So as we have discussed previously, A nodes with no children. So this particular D, E and F. So here we can say both the parts of node are null here also and same is this for. So all nodes D, E and F are called as a leaf nodes. Okay. Okay. So binary search tree which follows all the rules of binary tree that we have discussed. So what is binary search tree, right? So in binary search tree, the first node directly becomes a root node, okay? And the left child is always less than the parent node. And the right child of binary search tree is always greater than a parent node. So just to try this, understand this concept, we can go through one example, that is construct binary search tree for the following inputs. So as we have said, the first input directly becomes a root node. So we'll draw it as a root node 38. Now the next input is 13, right? So 13 is less than the root node. So it will go into the left side of particularly parent node. And here parent node is 38. So here it will, we can write the node 13. Then Next input is 51. So where will be the place for the 51? As 51 is greater than the root node, then it will go into the right side of particularly parent node 38. Next we have a 10, right? So we'll compare this particular value 10 with 38, right? So 10 is less than 38, it will go into the left side of particularly tree. Here again we'll compare 10 with 13, right? So 10 is less than 13, so it will become a left child of parent node 13. I hope you are getting these things. Then next we do have a 40. So where it will be? First of all we'll compare 40 with root node 38, right? So of course 40 is greater than 38, so we'll go into the right subtree. Again this particularly 40 will be compared with 51, but we know that 40 is less than 51, so the left child is always less than the parent node. So this is the right place for the node 40. Okay, so similarly we can insert 84. So where will be the place for the 84? See, 84 is compared with 38, right subtree. Again 84 is compared with 51, and finally it becomes a right child of 51. Similarly the next node is 25. So 25 will be compared here, then here, and it will become a right child of node 13, that is the parent node. Then after we have 89. So where will be the 89? Is this is the right place? Yes, it is the right place to place the 89, because 89 is greater than 84 in the right subtree. Then afterwards we have 37. So 37 will be the right child of node 25. Okay. Then there comes a 66. So where will be the 66? So it will become a right child of 51, right? Here we compared, then it becomes a right child of 51, but right child is already there, that is 84, and the next value is 66. So what we will do? We'll just make it the left child of 84. Fine. And the last one is the 95. So we can easily guess what is the position for the 95. So 95 will become the right child of 89. This way we can test against the condition of binary search tree. See, here 38, all the nodes present at the left subtree are less than the root node, and all the values which are present at the right subtree are greater than the root node. Again, suppose we'll skip this part, we will just look out to this particular part. So check here in this particular subtree, right? All the elements which are smaller to the 13 are present at the left subtree, and all the nodes which are greater to the node 13 are present at the right subtree. So this is 25 and 37 which are greater than the node 13. And similarly for this is the right subtree, right? So to the left we are having all the nodes which are less to 51, and all the nodes which are greater than 51 are present in the right side of node 51. So these are the things we do have for the today's discussion. I hope things are clear to you. Thank you so much for patiently listening. Thank you.